Hi, and welcome to the glass plate. Today, in this example, we're going to take a look at a microbalance, but now for a sphere with steady state conduction of heat when there is in the sphere internal heat production. So this is the production of heat per unit of time per volume. That's why it has 3 dashes. Q is a constant which means it doesn't depend on the radius, on the position. The outside temperature of the sphere is at the radius kept at T0, T0. So this is the radius. And we would like to know for this problem what is the temperature distribution as function of R. As it's a steady state, we're going to use the heat balance in this form. And we need to have a clever choice, as always, of the control volume. Well, this can be solved because it is T of R, so a profile with the microbalance. And our control volume will be a spherical shell between R and R plus dr, which is difficult to draw in 3D, so I'll just draw a 2D, as we always do. R outside R plus dr. Heat is flowing in here, out there, and there is probably production because of this Q. So if I start equating my balance, but now fill in what I know, I have an inflow which is the Fourier form minus lambda dt dr at the inner sphere, the area 4 pi r squared, and there is an outflow which is the same what displaced. So at R plus dr, and has a bigger area through which it goes, because the radius is slightly bigger. Plus there is production, and that is heat per unit volume per second, so I need to multiply this Q triple dashed by the volume of this part, so kind of this dashed part. And that is a very thin spherical shell, and that has a volume of 4 pi r squared dr. You probably recall that from elementary calculus. Okay, like we did before, 4 pi is everywhere, can be taken out. This can be better written internally, and then it becomes an r squared, as here it's already stated that you should evaluate it at r plus dr. Lambdas are here, not there, so I'll divide by lambda, and I'll flip these two from position as minus minus is a plus, and this is the minus. If I do that, I get r squared dt dr at position r plus dr, that is this term, minus that term, and that is r squared dt dr, so the same function in essence, taken at position r, and there is a production term which is now Q triple r squared dr, and I shouldn't forget divide by lambda, so I've taken that out there. This is what we had in the lecture. The d dr of r squared dt dr. And that is thus equal, and this ends at 0, to minus Q triple over lambda r squared dr. But this dr I'm not going to write here, I'm going to divide left and right as I turn this into a dr. So what is originally dr here has been moved to that side and is inversely the dr here. Okay, now I need to integrate this one. If I integrate once, I get r squared dt dr equals minus q triple over lambda r cubed over 3 if I integrate plus an integration constant. You need to rework this one again because I need to integrate once more, but let's stop for a second here and think about what boundary conditions do we actually have. When we used rods, for instance this one, I had a boundary condition here and there, but a sphere has only one boundary. So there might be a problem, but actually it's not a problem, it's a bonus. Boundary condition 1, if I start listing them, at small r equals the outer radius, the temperature is fixed at T0. That's the only boundary condition in a literal sense you can find because there's only boundary. But there's another one. There's symmetry around r equals 0. How can you use that? At r equals 0, whether you move in that direction or that direction, that doesn't matter. Or that direction and that direction if you want. Which says that heat cannot flow in any other direction. Cannot move. Because if you say it moves in that direction, exactly at r is 0, then why not at that? Because they are completely symmetric. So that means that dt dr, let me take another color because this one is not really writing. dt dr at r equals 0 must be 0. Symmetry. Oh, but I can use it immediately because if I put in this relation r equals 0, then on this side is 0, here is a 0. Actually all I need to know that it is finite. That tells me C1 is 0. Oh, but now this can be reworked with C1 is 0 to something that is very easy to integrate. R squared goes under on that side. So I'm left with the dt dr equals minus q123 lambda. R cubed over r squared is r over 3. And this is readily solved. T of r equals minus q123 over lambda r squared. So that brings in an additional half. This becomes a 6. And an additional boundary condition required of the C2. The boundary condition is found from the top one that I haven't used here. If I plug that in, T0 equals minus phi 123 over lambda r cubed over 6 plus C2, and thus you read off C2 as T0 plus this, and I can write TR, my final solution, equals T0, temperature at the boundary, plus Q123 over 6 lambda multiplied by r cubed, capital R cubed, minus small r cubed. Does this make any sense? Sure it does. Lowest point of this temperature curve is when this term is 0. That is 0 at r equals capital R, and then you arrive at T0, sure, because I put in that myself. Moreover, what is the hottest point? Well, when this is maximum, and that is r equals 0 in the center, and then this is at its maximum level. Which makes sense. If you start producing heat, this point, or the area around it, needs to lose that heat as well. It can only do so if it's warmer than its neighbors, and so on. So the maximum must be in the center. And actually, this states that this is a maximum, or a minimum, and we back out its maximum. Take a good look at the flow of the math. And try and see that we always do the same trick. These microbalancers boil down to the same. The catch is, carefully think about the areas. Are they constant, so I can scratch them out as the letter A, or are they depending on where you are? In other words, are they depending on the coordinate? In that case, you need to work that out. That's what I did here. Try this yourself for a cylinder that is solid, internal heat production, walls fixed in temperature, and try and solve. Good luck!